Module 4, Key Analytical Planning Issues, MQOs and APSs. Slide 1. Module 4 deals with Key Analytical Planning Issues, APS. Specifically, we will be discussing Measurement Quality Objectives, MQOs, and how to prepare an Analytical Protocol Specification, or APS. Slide 2. I worked at a nuclear power plant for 22 years as a chemist. In those years, I had some very strange things appear on my desk. During one of our refueling outages, a Ziploc bag shown here with mud, stones, and wire was on my desk when I arrived at 6 a.m. for the morning shift. The attached note from JR was all the information I received. Fortunately, I knew that JR was a system engineer working night shift, and he evidently had pulled this material out of one of the plant systems. Since he was working on the secondary side of the plant, it was a good guess that it came from a feed water heater. It is important to note, at this point, the secondary side of the plant had been contaminated with primary water the previous fuel cycle, and there was residual radioactivity on the secondary side. The heaters were all labeled potentially contaminated, but the heater was outside the radiologically controlled area and did not have continuous health physics coverage. I called him and confirmed my assumption. He wanted to know, what is the material made of and where did it come from? I performed a quick visual exam. I told him rust from inside the condenser and the preheaters forward of this one. What about the chunks, he asked. I took out a microscope and prepared a slide and called him back. It appears to be weld wire and weld slag, I said, after the microscope inspection. What about the scaffolding material, he asked. I asked, what scaffolding material? He said there was about 40 feet worth of scaffolding from the last outage that was unaccounted for. What was it made of, I asked. Aluminum, was the reply. I told him I'll need a couple of days to analyze for aluminum since we need to make a new standard and calibrate the atomic absorption instrument. My desk was outside the radiologically controlled area, and I needed to bring the sample into our primary laboratory inside the radiologically controlled area. When I brought the sample to the lab, I did a quick 20-minute gamma spectrometry analysis to see if the sample was contaminated. Sure enough, it contained cobalt-60 and cobalt-58. When I told this to the engineer, he said, that's interesting, but not important to what I need to know. The engineer's project was to find out what the material was made of to determine if it came from staging. What specifications should he have made about the sample so that the analytical process would have proceeded more smoothly and also provided information for my own personal safety? These are the topics that will be part of the Analytical Protocol Specification. Slide 3, Overview of the Analytical Process. The project manager needs to ask the right questions and ensure that the questions that relate to the sampling, transport, preservation, sample processing, detection limits, uncertainty, reporting requirements, safety issues, and other issues are all addressed by an appropriate subject matter expert. All of this seems very obvious, but in reality, it is seldom done. All of these pieces that lead up to the final analytical result must also ensure that they will be useful for making decisions and that the data quality objectives of the project have been met. Slide 4, Key Analytical Planning Issues. The project manager is responsible for the vision and entrusting his team specialists to find ways to implement the mission. All individuals involved in the project need to know what we see as the end result so that the steps from sampling to final data analysis can support the data quality objectives. We're going to discuss the key planning issues discussed in Chapter 3 of MARLAP. These issues will then be written into a single document called the Analytical Protocol Specification, or APS. Slide 5, Analytical Protocol Specifications. The APS represents the resolution and documentation of key analytical planning issues, many of which will be covered in this session. The APS is the culmination of the directed planning process. It assembles all of the requirements and presents it to all the stakeholders for their concurrence. Slide 6. The APS will contain any project that requires radioanalytical results. Submit samples to a laboratory that they have confidence will provide the correct results. The laboratory is always confident in their capabilities. However, the laboratory is seldom informed of all the requirements that a project has and often does not know how the sample was obtained or exactly what is contained in the sample besides the radionuclides they have been asked to quantitate. The APS provides the laboratory with all the information about the sample and about the project requirements. A concept central to meeting the DQOs of the project is that samples will be analyzed, ensuring that the required method uncertainty will be met for each sample. It is important that the APS is completed before samples are collected or analyzed and used for support of the data quality objectives and the decision-making process. The bullet items listed here are key parts of the APS. Note that the required method uncertainty is highlighted in red for emphasis. This is the main measurement quality objective and the key to the entire MARLAP process. Slide 7. Types of key analytical planning issues. The next segment of the presentation deals with the specific items which need to be considered, detailed, or eliminated when writing an APS. The general questions that need to be addressed in the APS are: what are we looking for? Simply saying we are looking for radioactivity or we want to perform a background measurement is not specific enough. The list of specific radionuclides needs to be decided upon. How high and how low in concentration will these radionuclides be able to be analyzed? The answer to this question will determine which laboratory and type of analysis will be necessary. Will a specific chain of custody be needed, and will the samples be required for evidentiary purposes? If legal issues are based on the results of the analyses, a very formal chain of custody with specific instructions and sign-offs will be needed. What matrices will be required to be sampled? Keep in mind that solid, liquid, and gas are states of matter, not matrices. Liquids fall into many categories that will require different types of analyses. For example, drinking water, stormwater, fracking liquids, and sewage effluents are all water samples, but each presents a separate concern in terms of how to treat the sample. If soil samples are to be part of the project, do they need to be homogenized? Who does it, the field sampler or the laboratory? And by what method and to what mesh size will the samples be homogenized? As you can see, there is going to be a substantial list of questions regarding each type of matrix and each radionuclide which will need to be addressed. Slide 8. Analyte list, general information. So let's get into some specific details of each of many issues that need to be addressed in the APS. MARLAP section 3.3.1 asks the question, which radionuclides are we looking for? There is an overall reason for performing this project based on basic knowledge gathering of a public-private concern. There are 2,540 radionuclides and 480 isomeric states of nuclides. The selection of what could possibly be in the site that is being assessed would be based on the radionuclide's half-life, how long before the site assessment the production or use of the radionuclide was present, and how much was there at any one time on the specific site. This encompasses the what was processed at the site and the historical site assessment. This may mean looking back tens to 100 years or more to find out what occupied the site in question. Are there previous studies that have been done on this site or on sites that had similar commercial or private processes? Have any preliminary project studies using screening techniques or general sampling been done? Keep in mind that these samples would not be considered project samples. They would be used as information to direct the planning process. Slide 9. Concentration ranges, general. MARLAP 3.3.2 discusses the anticipated concentration ranges of the radionuclides expected to be encountered. What are some reasons to anticipate why we need to know how much is present? Safety to samplers, safety to analysts, field versus laboratory analyses that may be necessary, potential laboratory methods to be used, costs of the analyses, and the sample size. Every single one of these items need to be addressed in the APS. Slide 10. Matrices of concern. MARLAP section 3.3.3 goes into matrices and questions about the matrices that need to be addressed. What are examples of matrices that the project will need to consider? Will or should the samples be homogenized in the field or by the laboratory? What are the contaminants in this matrix besides what you're looking for that may prove hazardous? For example, PCBs, explosives, for example, hydrogen in a tank of water, volatile organic carbons, carbon monoxide, etc. Solid, for example, is not a matrix. Humic, sand, clay are different descriptors for soil. Are the stones, twigs, roots, and other detritus in the soil actually part of the sample? Linoleum, what's it made of? Does it contain asbestos? The lab needs to know so that they can analyze it successfully and safely. Does the groundwater sample need to be filtered? Does the sandy soil sample need to be sieved? Must the whole sample be used? Must the whole sample be dissolved? These are the important questions that need to be answered in the APS. Slide 11. Relationships among the radionuclides of concern. MARLAP section 3.3.4 asks the project group to determine if there are important radionuclide relationships to consider. If medical waste is present and Tech-99M generators are part of the waste, what might be present that most likely will be undetected by gross alpha, gross beta analysis? Tech-99, the ground state of Tech-99M, will be present. It has a half-life of about 200,000 years and emits a very low-energy beta particle. It is important to the successful analysis of the sample to know if parent-daughter relationships exist, plus process knowledge for the site under investigation. As an example, a site produced lead-205 by neutron bombardment of lead-204. What else might you expect? Thallium-204 may have been produced from the side reaction lead-204 NP thallium-204. The thallium-204 has a half-life of 3.8 years. Will it still be present? Slide 12. Project resources and deadlines. What are the project resources and their specific deadlines or milestones that need to be achieved? Does a validated method exist for the analyte matrix, or does one need to be developed, and can it be done within the scope of work of the project? Contract laboratories rely on clients having samples that need to be analyzed. If they have an existing method for the radionuclides of your project, they may reply, "We can do it." But do they have a validated method for the radionuclide in your sample matrix? They routinely do strontium-90 in drinking water, but have never analyzed fracking liquid waste. The method for drinking water can't be used for fracking liquids. Can an off-site laboratory get the results to the decision makers in a timely manner, or will an on-site lab be needed to be established? The project requires a turnaround time of 3 days for all analyses, but the contract lab can only give a 10-day turnaround time. Need to find another lab or build an on-site laboratory? That's the question you have to ask. Will the funds available support the deadline based on the types of samples and analyses? In initial phases of the project, the time frame to get results may be shorter and require less precise measurement. As the analyte and matrix list is revised, the time to obtaining results may change and measurements may need to become more precise. Slide 13. Refine analyte and matrix list. Initially, you may know there is radioactive contamination. This could be one of 3,000 plus possible radioactive substances. As more information about the site becomes available, this list is pared down and the number of potential radionuclides and possible matrices decreases. This should be done at routine intervals in the early stages of the project and less frequently as time progresses. One approach that may help to pare down the list is to examine the possible dose consequences of radionuclides that are present and eliminate those that have very insignificant overall contributions to dose based on their expected concentrations. This decision, of course, should be documented in the project reports so that it may be revisited if necessary. Slide 14, Method Performance Characteristics and Measurement Quality Objectives. The method performance characteristics for each radionuclide in each matrix can have a profound effect on the measurement quality objectives that the project has elected to use. The most important characteristic MQO will be the required method uncertainty. An MQO may be either a qualitative or quantitative statement for a particular method characteristic. This is where the project manager must hone the details of the project goals. The characteristics noted on this slide are critical to developing project MQOs based on the methods selected. This is the decision point in the development of the project APSs, where a knowledgeable individual in radiochemistry, specifically a radiochemical specialist, needs to be part of the project team. If you have two different matrices like groundwater and concrete, and you need to analyze for strontium-90, the use of the same method for each matrix is likely an incorrect decision. Each analyte matrix pair should have its own set of MQOs and a separate APS for each analyte matrix combination. Slide 15, Example MQOs for Select Method Performance Characteristics. On this slide, we have provided two examples of specific measurement quality objectives. The first is an MQO for a minimum detectable concentration, 0.5 picocuries per liter for cobalt-60 in each water sample. Note there is an emphasis on the MDC being an MQO for each sample. The second example is for the required method uncertainty. The method for this, based on the program documents used for this project, was 2 picocuries per gram at the action level in soil of 20 picocuries per gram. Note here that this is the a priori method uncertainty MQO. Each sample that is analyzed will be required to have an a posteriori measurement uncertainty that is equal to or less than 2 picocuries per gram. Slide 16. Limitations on analytical options. MARLAP section 3.3.8 discusses the limitations on analytical options once the project MQOs have been established. The site historical assessment may be able to provide information regarding any radiological or non-radiological interferences that need to be addressed by the method selected. For example, significant quantities of thorium-232 can be determined directly by gamma spectrometry using the 911 keV gamma ray from actinium-228, as long as there is confidence that the actinium is always supported by thorium-232 in the matrix. However, the presence of cobalt-60 would cause significant background problems due to the Compton peak from the 1173 keV gamma ray in that region of the gamma spectrum. This limits the analytical options to methods other than gamma spec if the MQOs cannot be achieved due to the presence of cobalt-60. Slide 17, Method Availability, Matrix Specific. Method validation is a concept that deals with laboratories' experience with the method for the particular analyte in the particular matrix for your project. A method for your radionuclide matrix combination may not be available and will need to be developed. Any laboratory that is selected for a project sample analyses needs to be able to show that they have a method for that radionuclide in that matrix and can show you the data that proves how they validated their method. If your project requires weekly analysis of concrete samples for uranium, and the lab only performs uranium analyses once per quarter, decisions have to be made. Will the laboratory perform the analyses more frequently based on your sample load, and will the project be able to cover the increased cost by the laboratory for more frequent analyses using the current project budget? Or can the frequency requirement for the analyses be reduced to meet the laboratory schedule? Does the project management need to find a different laboratory to do the analyses on their current sample schedule? These decisions should be part of the project APS. Slide 18, QC samples, types, and frequency. Any or all of these QC samples may be chosen for the project. The radiochemical specialist, in coordination with the project team, needs to decide which ones should be used. The first four will be discussed in more detail in Module 10, where we will discuss acceptance criteria for each of these quality control samples. A performance evaluation testing sample, an external program, is not considered a lab QC sample, but it is an important part of the laboratory QA program. External samples like performance evaluation samples provide additional assurance that the laboratory QC program is working effectively. The matrix spike duplicate is usually not considered as necessary in radiochemical analysis, as radiochemistry has an independent means of assessing the yield of an analysis through the use of a carrier or a tracer. The radiochemical method should require chemical equilibration between the carrier or tracer and the analyte prior to any chemical separations. The use of a matrix spike duplicate would fall under the purview of the specific project documents. Slide 19, Sample Tracking and Chain of Custody. After samples are obtained, they may need to be stored prior to shipment, and once at the laboratory, also stored prior to analysis. The following questions should be addressed in the APS. Are the samples to be locked up? Should the sample be refrigerated? Who handled the sample? Must each person verify sample in their custody? What about shipping requirements? Are all containers sealed with tamper-proof tape? Does the original chain of custody need to be returned to the sample site? How is the chain of custody achieved at the laboratory? Slide 20, Data Reporting Requirements. There is no standard report format. The project team, using the APS, must let the lab know the project data requirements. The units of reporting and the number of significant figures in each result required by the project must be stated in the APS. There are many different ways to calculate the minimum detectable concentration, MDC, critical level concentration, or the minimum quantifiable concentration, MQC. The APS must state how the project team has decided these should be calculated so that the laboratory can conform to the project needs. What are the two ID numbers required on a report? These numbers cross-reference the project sample numbering system with the laboratory's sample numbering system. These are the project ID and the lab ID. Analyses don't always go completely as laid out in the method. Any anomalies for each sample analysis must be part of the report from the laboratory. The laboratory also needs to supply enough raw data so that some percentage of the calculations that they perform can be verified during the data review process. Slide 21, Matrix-Specific Issues. Section 3.4 of MARLAP deals with matrix-specific issues. How can the sample container affect the results? For example, filter papers stored in plastic containers, like a Petri-style dish, can cause the dish to develop a static charge due to the ionization caused by radioactive decay particles. This ionization could dislodge particles from the filter paper, causing spread of contamination and biased results. The issue of subsampling in the laboratory is usually not addressed adequately. The APS must specify how the sample is to be subsampled if the whole sample is not to be analyzed. Alternatively, if the laboratory has a subsampling method, it must be reviewed by the radiochemical specialist to ensure that it is appropriate for the project samples. See MARLAP Appendix F in Volume 2 for guidance. For any sample, if there is stuff included with the sample that is obviously not part of the sample, what should the laboratory do with those materials? For example, roots, twigs, large stones in a soil sample, are they part of the sample or are they to be removed prior to analysis? Is the radionuclide concentration in soil to be reported on a dry weight or a wet weight basis or as an ad receiver basis? These are all questions that must be addressed in the APS. Slide 22, example of an APS. Let's go through a specific example of an APS that has been written for strontium-90 in milk. Using the next several slides, we will review the details of this APS. Please open the file strontium-90 in milk APS and have it handy to follow this discussion. Slide 23. What do we know about strontium in milk? Knowing that we are dealing with milk, we need to describe the potential interferences. These can be radioactive or non-radioactive, such as calcium, milk fats, potassium-40, other fission products, and magnesium. What are the anticipated concentration ranges that need to be measured? What is the expected picocuries per liter that will be found in milk? Based on recent atmospheric samples, there is still strontium-90 in the atmosphere from nuclear testing during the 1970s. Thus, the concentration of strontium-90 in milk is probably not zero. What is the historical background for strontium-90 in milk? Are there other sources besides nuclear fallout? Are there any other facts the laboratory needs to know about strontium in milk that may be included in the APS description? How about describing the collection procedure? How is the milk preserved until the analysis needs to be performed? What type of dairy animal has been sampled? Cow, sheep, goat, yak? Should the lab be told of anything we know about the pasture used for grazing? The answers to these questions usually will provide valuable information to the laboratory. Slide 24, the basics. I'm going to read the title of a specific section on the APS, then pause so you can find it before I continue. Refer to the APS on strontium-90 in milk. Analyte list. Note, only one analyte is listed. The only exception might be gamma spectrometry, since only one final sample test source and only one counting method is used. Matrix. Note, only one matrix is listed, raw milk. Each APS should contain one specific for each radionuclide. Upper-lower concentration range. Based on the historical data, the concentration range expected is listed here as 1 to 50 picocuries per liter. Action level. The project team has determined that the action level for the milk samples is 8 picocuries per liter. Method validation level. The method validation level is decided upon by the Technical Evaluation Committee depending upon how different the project matrix is from methods that have already been developed by laboratories being considered for the sample analysis. Level A indicates that the laboratory already has a satisfactory method that they have documented data for, and it has been reviewed by the Technical Evaluation Committee. The validation levels get more stringent as the values go from A to E. For level E, a method validation reference material must be used by the laboratory to prove they can achieve the project MQOs before a contract is awarded. This will be discussed in more detail in Module 9. MQOs. The required method uncertainty at the action level is 0.5 picocuries per liter. Also, a relative required method uncertainty of 6.25% if the analysis yields a value greater than 8 picocuries per liter. Analysis limitations. This section tells the laboratory that a direct measurement of the analyte is required unless equilibrium of the progeny with the parent can be assured following chemical separation. In other words, chemical separations are necessary to ensure the only radionuclide being measured is strontium-90 or its progeny, yttrium-90. Possible interferences. The presence of other beta-emitting fission products or any naturally occurring beta emitters like radium-226 progeny can cause significant interference. It is important to recognize the amount of detail shown on this first page. This is just the beginning of what the laboratory needs to know. Slide 25. What methods meet the MQO? Before we continue with the rest of the APS, let's examine the MQO and some potential methods that could be used for this analysis. 3 potential methods have been proposed by different laboratories. The Technical Evaluation Committee and the radiochemical specialist need to assess the 3 methods and their method validation documentation and determine which methods meet the APS specifications. I want to emphasize here that the required method uncertainty, U sub MR, is for 1 sigma, LCS is liquid scintillation counting, beta detector is a zinc sulfide crystal detector, and GPC is gas proportional counting. It is clear from the data shown that the laboratory using the beta detector should not be selected as it cannot achieve the required method uncertainty. However, the method validation studies that were performed on the other 2 methods must be reviewed by the TEC to make sure that the milk matrix was used for that study. Slide 26. Stipulation of quality control. Referring back to the APS, we see that the type of QC and the frequency has been specified. Looking at attachment B to the APS, we can see that the evaluation criteria for the laboratory QC samples for each batch of our samples is specified by the TEC in this APS. Those acceptance criteria are based on the required method uncertainty for the analysis of these samples. Thus, we have connected an important measurement quality objective requirement of the project to the data being produced. These will be further elaborated when we discuss Chapter 7 of MARLAP. Slide 27, Analytical Process Requirements. The analytical process requirements start with the actual field sample preparation and preservation. In this instance, the sample is to be greater than 3.5 liters and either preserved with ice or with 5 milliliters of 37% formaldehyde per liter of sample. The sample receipt and inspection by the laboratory has specific instructions and written reporting requirements to the project organization. Here, the project team has asked that the samples be surveyed and the results reported back to the project team on the chain of custody form. The laboratory sample preparation contains specific information that the project team deems important to the overall analytical process. Note here that gamma spectrometry will also be done on this sample. That means that there will be a separate APS for that analysis. Slide 28, Analytical Process Requirements, continued. We continue the discussion of the APS requirements on this slide. For sample dissolution, none is listed. Does that mean that acid digestion can't be done? No, but the method proffered by the laboratory must show that acid digestion of milk has been validated by the laboratory. Remember, this is a performance-based requirement. The option of using ion exchange or precipitation to separate out the strontium has been considered by the project team, and either method is acceptable. Several methods of nuclear counting have been listed, but the method must accommodate for the presence of strontium-89. What is the significance of the chemical yield requirements being distinct for strontium-85 tracer versus strontium carrier? This is to minimize the uncertainty due to excess mass from calcium carryover in the method, causing a higher yield and ultimately underestimating the strontium-90 concentration. Such an underestimate would be non-conservative when assessing potential dose to the target population. Ultimately, the requirements here minimize uncertainty in the yield and also the counting method due to the potential self-sample absorption. Slide 29, Attachment A, Data Reduction. Attachment A of APS is detailed in pages 2 through 4 of the handout. These pages detail the calculational and quality control requirements. The calculational and quality control requirements ensure that the MQOs of the project will be met. The laboratory may have different quality control acceptance criteria and sample result calculations that they use, but those do not necessarily meet the project measurement quality objectives. Note that these are examples of what could be requested by the client. Item 3 specifically discusses that the MDC is a sample-specific minimum detectable concentration versus a method minimum detectable concentration. Note, item 3 does not discuss the use of an yttrium yield. Is this an oversight? Is an yttrium yield necessary? See Data Reporting section, item 1. Item 4 says that the critical level will be calculated on an individual sample basis. Item 5 requires that the analytical laboratory report include the calculation steps for each sample with the sample's specific parameters used for each calculation. The rest of the APS deals with data reporting issues and how to calculate quality control acceptance criteria. While the laboratory may have its own acceptance criteria for QC samples, each analysis must be verified to meet the criteria specified here. Page 5 of the handout is part of the APS and notifies the laboratory of the method validation requirements. This is necessary so that if the laboratory finds that it is necessary to modify their method, these are the requirements for your project's method. Slide 30, Attachment A, Data Reporting. These are examples of what details of the sample data could be requested by the client. There are additional factors that could be requested, such as certificates for standards used, trend graphs for all QC results, trend graphs for specific analyte recoveries, copies of condition reports or laboratory incident reports that may affect the sample processing, etc. Slide 31, Wrap-Up. Because the APS documents the resolution of the key analytical planning issues, it is critical that the whole project team review the APS to ensure that the projected results will meet their specific needs. The APS must be done before any samples are analyzed that will be used to support the DQOs and MQOs of the project. There should be give and take with the laboratory so that the requirements in the APS are not overly restrictive but still meet the project objectives. The MQOs should have already been selected and approved by all stakeholders so that when results begin to accumulate, there is no question as to whether the measurements really mean. The data validators and verifiers and assessors should use the APS to ensure that the results have met the required needs of the project. Slide 32, Class Activity on APS. The best way to show yourself that you can use the information in this module is to have you write your own APS. There are two files that you have access to. One is titled APS Template, a Word file, and the other Tritium APS Solution, a PDF file. Proceed to slides 33 and 34 and the RAD scenario. Slides 33 and 34, Tritium and Concrete Scenario. The scenario deals with the analysis of concrete that has been saturated with water that contain tritium. Open the APS template Word document and fill in the requirements listed on slide 34. Keep in mind that you will need to use not only the information provided in this lecture, but also from lectures 2 and 3. Once you have completed your APS, open the PDF file Tritium APS Solution and check your answers. Slide 35. MARLAP recommends. The following are the recommendations made in the MARLAP manual regarding the APS. 1. Assumptions made during resolution of key analytical planning issues be documented. 2. Each radionuclide has an action level and a gray region. 3. MQOs be established for each select method performance characteristic. 4. An MQO for method uncertainty should always be established for each analyte matrix combination. 5. That all measurement results be reported directly as obtained, including negative values along with the measurement uncertainty.